Hi, my name is Andy, and I'm a biochemistry major of the class of 2018.
And my name is Callie, and I'm a biochemistry major of the class of 2019.
Today we will be walking you through Skill Builder number 9 from Chapter 6. The problem says, after studying the absorption spectra of this dye, it was found that it had a maximum absorption at 575 nanometers. Part A says, calculate the frequency of this wavelength. Part B tells us to calculate the energy of this wavelength. And C says, based on the physical appearance of this dye, what color does the absorption at 575 nanometers correlate to? Please pause the video and attempt it first by yourself. The formula for the energy of a photon is E equals h nu. H is Planck's constant and nu is frequency. Planck's constant, or h, is 6.626 times 10 to the negative 34 joules times seconds. Frequency, or nu, is defined as inverse seconds, so the seconds cancel out to give us an energy in joules. We can also define frequency as c over lambda, where c is the speed of light, and it's 3 times 10 to the 8th meters per second. And lambda is the wavelength of our light, and it is measured in meters. We need to make sure we convert our wavelength of light from nanometers to meters so that it cancels out to give us a frequency in inverse seconds. We can now substitute frequency, or c over lambda, into this energy equation to get an overall energy equation of E is equal to hc over lambda, where we have Planck's constant times the speed of light divided by the wavelength of that light. Part A asks to calculate the frequency of this wavelength of 575 nanometers. We first need to convert 575 nanometers into meters, so we multiply by a conversion factor of 10 to the negative 9 to get 575 times 10 to the negative 9 meters. To calculate frequency, we know that frequency is equal to c over lambda. C is 3.0 times 10 to the 8th meters per second, and our wavelength is 575 times 10 to the negative 9 meters. So meters cancel out, and we get a final frequency of 5.22 times 10 to the 14 inverse seconds.
Part B asks us to calculate the energy of the light. To calculate energy, we can use the equation E equals h nu, using the nu that we just calculated in Part A, which is 5.22 times 10 to the 14th inverse seconds, and Planck's constant, which equals h equals 6.626 times 10 to the negative 34th joules times seconds. Now we can plug this into the equation with energy equals Planck's constant 6.626 times 10 to the negative 34th joules times seconds times nu, which is 5.22 times 10 to the 14th inverse seconds. And canceling seconds, we are left with energy, which is 3.46 times 10 to the negative 19th joules. And we can see that the unit for energy is in joules, and this is our answer. Part C asks us to find the color of this dye that absorbs a wavelength of light of 575 nanometers, or light with an energy of 3.46 times 10 to the negative 19th joules. If we look at a table relating the frequency and wavelength of light to the color of light, we can see that a wavelength of 575 nanometers corresponds to yellow light. However, we need to remember that this is the color of light that is absorbed by the dye, not the color of the dye. If we look at a color wheel, we can see that if a compound is absorbing mostly yellow light, or has a wavelength max in the yellow region, it will be reflecting violet light the strongest. Since the dye is reflecting mostly violet light due to the high absorbance of yellow light, we can conclude that the dye has a violet appearance.